So I'm back in the classroom. I hate this. Like, I hear everybody waking up from their naps business and then crying, and it's very upsetting to me. All right. Recording. Sorry. This was number 1 on the quiz that we were just talking about. Let's see. Okay. Number 2. Rewrite the integral by completing the square. This is a straight up algebra question that I asked you on your Calculus 2 quiz. I mean, it's in disguise as a calc question, but I didn't actually ask you to do any calc. I'm just asking you to complete the square. So you'll have 3x squared plus 6x minus 5. Remember that you are going to leave the constant alone. You're going to factor out of the first 2 terms. 2x. Like that. And then you're going to ask yourself, what do I need to add to this to make it a perfect square trinomial? Well, half of 2 is 1, and 1 squared is 1. And then you're going to be really careful because you didn't just add 1, you added 1 times 3. So if you added in 3, you must also subtract 3. And then you can factor that as x plus 1 quantity squared times 3, and then subtract off 8. So that was question 2. Does anyone have a question about that one? And then number 3, rewrite the integral to use partial fractions. So I was in the office hour today and somebody said they had just started the homework for 7.5 and didn't realize the question was asking them to do long division. And secretly I wanted to be like, I'm so glad you started that because now it's going to be fresh in your mind that you're going to have to do long division here. Here's what it looks like. I should say number 3 instead of, I don't want it to look like it's quiz 3. All right, so 5x cubed plus 1 divided by x squared plus 5x plus 6 dx. And I even was tricky and I gave you a distractor that you would have gotten if you did not actually perform the long division that you needed to do. So let's see. Remember that if the degree of your numerator is greater than or equal to the degree of the denominator, you must perform long division first. You can only use partial fractions when you have a proper fraction here. In this case, you have an improper fraction. You're going to have to make it a proper fraction by making sure that the degree in the numerator is less than the degree in the denominator. We'll do some long division here. Don't forget, it's most helpful to fill in your missing, if you want to call them place values. But you don't have an x squared, you don't have an x, you can zero those out so you don't lose track of what's supposed to go there. And then divide by x squared plus 5x plus 6. You're going to take the first term in your dividend and divide it by the first term in your divisor. So 5x cubed divided by x squared is 5x. And then you're going to multiply the first term in your quotient by every term in your divisor. So this leaves you with 5x cubed plus 25x squared plus 30x. And don't forget that when you're using long division, you're always subtracting. And, you know, go through and double check and make sure everything is where it's supposed to be. Make sure all your powers are still descending. Otherwise, something has gone wrong. If you've done this correctly, your first terms are always going to be additive inverses. So those are gone. And then you'll have 0 minus 25, which is negative 25x squared. And 0 minus 30 is negative 30x. I didn't take the time to sit here and go through and make interesting distractors based on all the places I thought you would have gone wrong. I made these very boring, but Sorry, maybe that's a good thing because maybe you'd be like, wait a second, this doesn't make any sense. Not even on here. All right, now you're going to repeat the process as long as these degrees are the same or this degree is one more than that one or any more than that one. So negative 25x squared divided by x squared is negative 25. And then you'll have negative 25x squared, negative 125x minus 150, and subtract. So negative 25x squared plus 25x squared, if you've done this correctly, you're going to get 0. Then you'll have negative 30 plus 125, which gets you to 95x. And then 1 plus 150 is 151. So this is probably the one that took you the most time on the test. Not the test, the quiz, I should say. So when you rewrite this, you'll get, sorry, I'm writing this wrong. All right, 5x minus 25, that's your quotient. And then you're going to add in the remainder, which is 95x plus 151 divided by the divisor. So this is going to be plus 95x plus 151 divided by x squared plus 5x plus 6 dx. And then here's where your partial fractions are going to come in. And these are pretty straightforward. I was going to make it some sort of crazy quadratic, but I decided we'll leave it simple with the linear since we're throwing in the long division with this. You can split this up if you'd like. If this is distracting you, split it off into a whole nother integral. And then what you're focusing on at this point is this one. And if you want, you can even factor this now because you're going to need to factor it anyway. So the two numbers that multiply to 6 and add to 5 are 2 and 3. I did give you distractors with, I think, 1 and 6, but that's just because people always factor this wrong. I don't know. It's like a mental thing. Your mind just sees the 5 and the 6, and it thinks 6 and 1. But that only works if you have different signs. If they're both positive, you're going to have to go with 2 and 3. All right, so here's where you're going to use your partial fractions, and this process is pretty straightforward. So you're going to have a over x plus 2 and b over x plus 3. And then it's up to you. I mean, personally, if I just have two linear factors, I'm just going to go for the simplest route possible, which is, to me, just letting x be negative 2 and then letting x be negative 3 to isolate a and b. But that's up to you. If you want to be consistent all the time and always use the matrix in your calculator with the RREF form, that's fine. Go ahead and do that. So I'm going to say let's let x be negative 2. And then, let's see, 95 times negative 2 plus 151 is negative 39 equals a times negative 2 plus 3. So that means a is equal to negative 39. And then do the same thing here. We'll let x be negative 3 so that we can get rid of the a term, and then we'll get b. So 95 times negative 3 plus 151 is negative 134. Then your a term is going to go, and you're going to get b times, well, negative 3 plus 2 is going to be negative 1. So that means b is positive 134. So when you rewrite your integral, when you come down here, you'll have the integral of 5x minus 25. And then your 95x plus 151 will turn into negative 39 over x plus 2 plus 134 over x plus 3 dx. something like that. I think that's the way I wrote it on the quiz anyway. Just I wanted it to look super straightforward so there wouldn't be any minus signs. I wanted it to be clear. 5x minus 25. Yeah, exactly. And then I just switched the signs and changed the denominators. I did give you one distractor where you would have gotten that same answer had you not actually performed the long division. And that answer would just be these two terms without the 5x minus 25 on them. Okay, someone mentioned to me that they were told midterm grades are going to be due before your second test. So usually the second test comes and then the midterm grade is due. I just submit them whenever I'm told to submit them. Usually I get an email reminder that says like your midterm grades are due by Monday or something, and then I just update them. But since we only have 4 tests in this class instead of 5, the length between the tests is a little bit longer. So it is highly possible that we won't have our second test yet before the midterm grades are due, especially since this is one of the longer chapters. So I am going to be updating homework scores. I just keep forgetting to do so. I don't know why it keeps entering my mind and I don't write it down and it just doesn't happen. Just because I guess maybe more pressing stuff comes up. I don't know. But I have a note now on my computer to update them in D2L. I mean, you guys know what your homework scores are. You can see them in Achieve. But I want to make sure everything's in D2L because some of you are going to freak out and be like, whoa, I had no idea my homework scores for the homework I wasn't doing were affecting my grades so much. What a bummer. I should probably start doing my homework. And that's the goal. So that's kind of why I feel bad that I haven't updated them, because technically you know that your homework is worth 20% of your grade, but I really want you to see how much that's impacting you if you're not doing your homework. And for the ones who are doing your homework diligently, your score is going to go up, because it's very likely that as long as you're doing the homework, you're getting the credit for it. I mean, you could easily be getting hundreds on your homework and you probably didn't get 100 on your test. So your class score is going to go up when I update your homework scores. It does make a big difference. I know it doesn't seem like a lot, but it does make a huge difference on your grade. Okay. Questions before we get into L'Hopital's rule?
Oh, I was just going to mention, I do a different way to complete the square. I don't know if anybody else does it. I use the vertex form parabola thing, the ax plus b squared plus e formula.
Mm-hmm.
I find it easier because then I don't screw up any signs or anything.
Yeah, I mean, it's basically the same process, but yeah, if you want to think about it that way, that's fine. As long as I see your work, that's all I care about. Any other questions or comments? Okay. I will probably just add this into the office hour notes. I couldn't figure out why my son's like piano playing was grating on me tonight, and it's because it's cool outside and the air conditioning is not running, so it seems so much louder. The AC just kicked on and I'm like, thank goodness. I love listening to him play piano, but it's very distracting while I'm up here. I need like a soundproof room. I should have had the school pay for that, right? That wasn't going to happen. All right. L'Hopital's rule, which is going to be a huge departure for us today. So if you were kind of looking for a break from the heavy integration, you're getting it now with L'Hopital's rule. We're going to be doing lots of derivatives today, and most of them are not going to be that complicated and looking at limits. It's actually kind of funny because I was just remembering like a month ago when you guys were like, oh, thank goodness we're out of chapter 6 and now we're into chapter 7 and this is so much better. And now you're kind of like in the thick of it in chapter 7 and you're kind of like, oh my gosh, all this integration's killing me. Let's do something else. Kind of like when you're doing these like arm workouts and they don't seem that bad. And then like all of a sudden you're like, oh my gosh, this is getting intense. I've been doing this same workout for like 5 minutes now. Let's switch it up. And as soon as you switch your movement, all of a sudden it seems like, oh, that wasn't too bad. And then you do that for 5 minutes and it's just like, oh my gosh, I'm going to die again. feel like this class is kind of like that. You go through something and it's like, ugh, like switch it to something else, and then we switch, and then it's sort of a relief. So hopefully, doing L'Hopital's rule today will give you a little bit of a just a little bit of a breather. Get a little bit of that fatigue to kind of calm down a little bit, subside. Okay. 4.5, L'Hopital's rule. Yes, 4.5. This is from way back in chapter 4. L'Hopital's rule. I had a really, really, really good student in Calc 2 semesters ago, and he always came to the office hours, and he was so sharp. But every time we would talk about this, he would be like, okay, so I was using L'Hospital, like L'Hospital's rule. I know it looks like hospital, but it's not hospital. It just looks like, come on, L'Hopital. So I'm telling you now, it's not hospital. It's not L'Hospital. L'Hopital. Okay. Let me give you a theorem here. Oh, I'm going to give you the one out of your book, actually. Oh my gosh, so many things. 4.5. Actually, before I give you the theorem, let's talk about when you would use L'Hopital's rule. Let's talk about indeterminate forms. Definition, indeterminate form. Now, you heard about indeterminate forms before in Calc 1, so if this sounds really familiar, you did sort of learn about what to do in indeterminate forms, but you had a different method, like an algebraic method to get rid of them. I'm going to remind you of what that is, by the way. Indeterminate form at C of the type 0 over 0 or infinity over infinity. So we spend a lot of time talking about evaluating limits and ending up with a form that's 0 over 0 or infinity over infinity. And we spend all this time on it. So if you get to the end and you find that your answer is 0 over 0, don't then say this. It's not true. So it drives me crazy on a test because I'm like, why did we spend so long talking about indeterminate forms just for a student to tell me that 0 over 0 is 0? Because it's not. It's indeterminate. That means that you cannot make a conclusion about the value of your answer. If the functions f and g are each defined in an open interval containing c, except possibly at c, then the quotient f of x over g of x is called an indeterminate form at c of type 0 over 0 if the limit as x approaches c of f of x equals 0 and the limit as x approaches c of g of x equals 0. So if you end up with values of your limits for both the numerator and denominator of your quotient that are 0, then it is the case that you have an indeterminate form of the type 0 over 0. It is the indeterminate form of type infinity over infinity if you have a similar situation. So we'll say indeterminate form at C of type infinity over infinity if the limit as x approaches C of f of x is infinity, and the limit as x approaches C of g of x is infinity. You guys hear the piano? Should I tell him to stop?
It's not too bad.
He's only 6. He's actually very good for being 6. He's not like a child prodigy or anything. But if it gets crazy, if my 2-year-old tries to get in on it, I'll have to yell at them. He's supposed to be practicing. It just is unfortunate that I'm remote. Okay. Okay. It's very distracting. All right. So those are indeterminate forms. We're going to be talking, though, about different indeterminate forms today. We're first going to be focusing on the 0 over 0 and the infinity over infinity. But I want to make sure, because I might end up, I forget to list them out, because the way your book has them listed out is actually pretty cool, the way they have it organized, but I'm worried that I'm going to forget. So note that you have other indeterminate forms, because I really like for you to have a list of them. So you have other indeterminate forms that are 0 times infinity. And I know that one is probably going to bother you because you're looking at this and you're like, well, isn't 0 times anything 0? But then you might be like, well, isn't infinity times anything infinity? So if you have 0 times infinity, that's an indeterminate form. And we'll talk about what to do when you have a limit that yields this form. We're going to be doing some rewriting there. Here's one that throws people. 1 to the power infinity. Everyone says that should be 1. It's technically indeterminate. I'd like for you to have a list because I want you to be able to recognize these when you see them, other than thinking about, like, is this indeterminate or not? Because sometimes it's hard to tell. 0 to the 0 power is indeterminate. That one I sometimes forget about. There's also infinity to the 0 power. Also indeterminate. And then one that you'll see probably more often than, well, actually you see a lot of these pretty often, but this is a special type of form where we're going to have to rewrite our function in a different way when you get infinity minus infinity. I know we think infinity minus infinity, it should be 0. No, not the case. I also want to note that 0 to the infinity is not indeterminate. It's actually equal to 0. I know. If you want, you could spend hours researching this online, because you might be thinking, well, if 0 to the infinity is 0, then how come 1 to the infinity isn't 1? That's a whole nother exploration that you can do if you're really interested. But 0 to the infinity equals 0, which means it's not indeterminate. Now, if you're thinking like, okay, fine, like, doesn't really matter, it actually does matter that you can recognize these forms, because you cannot just willy-nilly use L'Hopital's rule whenever you want to. You have to already have an indeterminate form in order to use the rule that I'm going to give you. So if you don't have an indeterminate form, you can't use L'Hopital's rule. It's going to change your limit. So you might want to make sure that these are highlighted so you can easily find them later, or if you're the kind of person who is building a note card as you go through, these are the things you're looking for. 0 over 0, infinity over infinity, and then any of these forms I just gave you, 0 to the infinity is not indeterminate equals 0. Yeah, so that's kind of the basis for what we are going to be doing here. I'm going to give you now L'Hopital's rule for finding limits that have indeterminate forms. So you're going to use L'Hopital's rule when you go to take a limit and you end up getting an indeterminate form. And like I said, I'm going to remind you of how you did these in Calc 1. I want to filter that I have this, like, take out the background noise thing on my, yep, it's okay. All right, so L'Hopital's rule. Suppose the functions f and g are differentiable on an open interval I containing c, except possibly at c. Suppose f and g are differentiable on an open interval I containing c, except possibly at c. And g prime of x is not equal to 0 for all x not equal to c in I. We don't want to divide by 0. So g prime of x is not equal to 0 for all x not equal to c in I. Let L denote either a real number or plus or minus infinity. And suppose f over g is an indeterminate form at c. Of the type 0 over 0 or infinity over infinity. If your limit of f prime of g prime is equal to L, then your limit is equal to L. So here's your conclusion. If the limit as x approaches c of f prime over g prime equals L, then your limit as x approaches c of f over g is also L. And there's a proof in your book for that if you're interested. All right, so I'm going to give you some steps that go along with this type of indeterminate form that we're going to be applying to the first several examples that I have to show you. So we're going to check to verify that f over g is an indeterminate form. We're going to first talk about this for being the type 0 over 0 or infinity over infinity. We're going to move into talking about the other indeterminate forms and some later examples, starting with example like 8 or 9. Some of these are pretty quick examples. We're going to differentiate f and g separately. So look at your definition. We're talking about the limit as x approaches c of f prime over g prime. That does not mean that you're taking the derivative of the quotient f over g. You're taking the derivative of f and dividing it by the derivative of g. Now, this would have been a dream come true for you in Calc 1, because in Calc 1, you never wanted to use the quotient rule. You just wanted to take the derivative of the numerator and denominator separately. Well, finally, this is your time to shine. You get to do that. Life is going to be good for you. If you end up in a situation where f is a quotient or g is a quotient, then yeah, you're going to have to use the quotient rule. But assuming that f and g are just polynomial functions or just some other type of function that's not a quotient, then you're just taking their derivatives separately. Then you're going to find the limit of the derivative of f over the derivative of g. So find the limit as x approaches c of f prime over g prime. This limit is equal to the limit of f over g, provided your limit is some number or plus or minus infinity. So if your limit ends up being just infinity or negative infinity or any number, awesome. Well, that means that you now have the limit of your function. So your function is going to have the same limit as the limit of the derivative of the numerator over the derivative of the denominator. Sometimes, though, you're going to have to apply L'Hopital's rule more than once. So if f prime over g prime is an indeterminate form at C, repeat the process. Okay. So you're going to see some examples where you're going to have to repeat the process. Every once in a while, you're going to see an example where you have to repeat the process like 9 times. But usually if something like that happens, it's because you have something like x to the 10th divided by like e to the x or something like that. And you just have to get that polynomial down to a constant. And by the way, you might be asked to find the limit at some value c where this form is not indeterminate, where maybe like if c was 0, it would have been indeterminate, but c ends up being some value that doesn't cause there to be an indeterminate function. So it does not have to be the case that you're always evaluating the limit at values of c that cause your form to be indeterminate. So pay attention to that. Step 1 is very important. Verify your form's indeterminate. Like I said, if it's not, then you're not going to use L'Hopital's rule. It's going to be invalid. And your homework questions, by the way, will throw in some examples here and there where the form is not actually indeterminate, and you can just use rules from Calc 1 to find the limit. So check it first. Some of them won't require L'Hopital's rule. Okay. So let's go ahead. I'm going to show you some examples for these specific forms of 0 over 0 and infinity over infinity. We're going to start out here with example 1. This is going to be the limit as x approaches 2 of the square root of x plus 2 minus 2 divided by x minus 2. Excuse me for this might look familiar to you if you took Calc 1 recently, because when you took Calc 1, you learned how to do this using algebra. So what we did was we plugged the 2 in for x, and you would take 2 plus 2 under the radical, minus 2, and then 2 minus 2 in the denominator. And then you would end up realizing that you had the square root of 4 minus 2 divided by 0, which ended up giving you 0 over 0. When you were in algebra, you went through this whole process where you would multiply by the conjugate. So you multiplied this whole quotient by the square root of x plus 2 divided by the square root of x plus 2 plus 2. Because I want you to use L'Hopital's rule here, I'm not going to actually show you how to use the conjugate. I don't want it to be confusing, like, wait, I remember her doing that, because it's not actually using L'Hopital's rule. What I'm going to show you now is how to find this limit using L'Hopital's rule, which means that we're going to be taking the derivative of the numerator and the denominator separately. When we do that, in some cases, you might have to use the chain rule. Either way, you're going to have to remember how to take derivatives. And for some of you, that's far back. I know we've been doing that with u substitutions as far as getting du, but a lot of them have been really straightforward polynomials. So we'll go through some examples here. Hopefully, all of that will come back to you if it's something you haven't used in a while. So this is an indeterminate form. So we're going to use L'Hopital's rule. To do that, I'm still going to take the limit as x approaches 2. And by the way, notice that if I was going to any other number instead of 2, this would not have been indeterminate. It's only indeterminate because I'm approaching 2. And then we're going to take the limit of the numerator and denominator separately. So if you'd like, first, if it helps you to write your square root as a 1/2 power, that's fine. Do that. If you even want to pull this out of your limit and work on it and then put it back into the limit, we're going to do that sometimes as well, just because sometimes you just have to keep remembering to rewrite your limit over and over. By the way, that reminds me, notice how I had the limit here and I dropped it when I got past this equal sign. As soon as you substitute that value in for x, you don't need to keep writing the limit at that point. You don't want to keep writing it. But as long as we have an x in our expression, I need to keep writing the limit here so I have my notation correctly written. All right, so the limit of the numerator, for the first term, we're going to need the chain rule. So we're going to bring that 1/2 out front, rewrite the inside function, and then decrease the power on the exponent by 1. So 1/2 minus 1 is -1/2. And then the derivative of 2 is 0. I mean, you don't have to write that. Just because it's the first example, I'm just going to put it down there so you know that I did, in fact, take the derivative of 2. And in the denominator, the derivative of x is 1. The derivative of 2 is 0. Okay. Once you've simplified this down, if you would like, you can rewrite it again. You can go ahead and evaluate it now if you'd like. It does not matter to me. You'll probably find this easier to evaluate, though, if you simplify it. Right now, with the negative exponent, it just looks kind of confusing. So before I evaluate my limit, I'm just going to simplify it. Notice we just have 1 in the denominator. If you had 0 minus 0 in your denominator, you'd have some trouble and you'd have to apply L'Hopital's rule again. So you might just want to do even a quick verification that you don't have an indeterminate form, which you clearly don't. So I'm going to move this x plus 2 to the 1/2 power into the denominator. The 1/2, I'm just going to write as 1 over 2, where the 2 is also in the denominator. And then in the numerator, that just leaves me with a 1. So this is not indeterminate. I can go ahead now and apply the limit to this quantity. Notice it cannot possibly be indeterminate because I have a constant in the numerator. So when you evaluate this limit at 2, you can just use your Calc 1 skills at that point and just directly substitute 2 for x, and you'll get 1/4. All right, questions there? Okay. So that was an example of a 0 over 0 indeterminate form. Example 2, we're going to take the limit as x approaches infinity of 7x squared plus 3x minus 3 divided by 6x squared plus 9. Again, you are going to verify you get an indeterminate form. You did a lot of stuff like this in Calc 1. Oh, by the way, if you did something like this in Calc 1, you probably remembered that we were talking about this in relation to horizontal asymptote rules from algebra. So in algebra, you weren't actually applying limits, but you were thinking about what happened to the function as x got increasingly small or increasingly large. And really what you were doing was applying a limit at infinity. If you remembered your horizontal asymptote rules, you remembered that we talked about what happens to the function if the degrees in the numerator and denominator were the same, if the degree of the numerator was less, or if the degree of the numerator was greater. You can double check your answer using those rules if you remember them from algebra. If you don't, that's fine. You're going to have to use L'Hopital's rule anyway. I want to see your work here using L'Hopital's rule. I also want to see that you verify that you have an indeterminate form. So if you were to do the direct substitution here, which I know seems kind of weird with infinity, but what you would have is 7 times infinity squared plus 3 times infinity minus 3 divided by 6 times infinity squared plus 9. And what you have here is just the series of infinities being squared and added to each other. And no matter what, an infinity squared plus an infinity is still going to be controlled by infinity squared. This infinity to the first power is doing much less to the function than that one. So you're getting an infinity in the numerator and also an infinity in the denominator. You're thinking of infinity squared as being infinity. So if some of these ideas are new to you, maybe you didn't explore them very much in Calc 1, we're going to be kind of moving into this train of thought a little bit more at the end of chapter 7. And as we move into chapter 8, things are going to be much more abstract, I guess, logical. Abstract and logical are different. But you're going to be thinking about things using different types of reasoning. And not all of it is stuff that you're going to be able to write down. Some of it is just going to be like, okay, I have this thought. You can write down what your thought is, but you could be thinking it in a completely different way as somebody else. Anyway, so you'll have infinity over infinity. Does anybody have a question about how I obtained this indeterminate form? Okay. Wonderful. Then let's use L'Hopital's rule, because I know that if I have infinity over infinity, that is not equal to infinity. It's definitely not equal to 1. I know we usually think of a quantity divided by itself as being 1. That's not the case here. We're going to go ahead and use L'Hopital's rule. It's going to be super straightforward, especially when you have just the quotient of 2 polynomial functions. Remember, you're not using the quotient rule here. Don't do a bunch of extra work that you don't have to do. We're looking at the derivatives of the numerator and the denominator separately. And you will get 14x plus 3 divided by 12x. Well, what happens then is if you were to evaluate this at infinity, you'd have 14 times infinity plus 3 divided by 12 times infinity, which again gets you to infinity over infinity. don't get caught in this mind trap where you're thinking like, well, 14 times infinity is more than 12 times infinity. I mean, infinity is the important thing here. The 14 and the 12 are immaterial, and adding 3 to it. So don't think that, oh, well, the numerator is greater, so it must automatically go to infinity. That's not the case. Anytime you get infinity over infinity, you must use L'Hopital's rule. Do it again. So the derivative of the numerator is 14. The derivative of the denominator is 12. In this case, you're just taking the limit of a constant. The limit of a constant is that constant itself. And you should definitely divide by 2 to simplify. Another thing I wanted to remind you of, because it's probably been a while since you've seen it. You can double check these on your calculator. Mine's probably not going to show up. Let me move my light a little bit closer. All right. Don't forget that you can check limits in your calculator just by entering the function and sort of getting an idea of what's happening to the function values as x gets increasingly large. You might want to just, get an idea of what 7/6 is close to. So you're expecting your limit's going to be approaching something like 1.17-ish. But you can always go to your y equals, and you can enter your function 7x squared plus 3x minus 3 divided by the quantity 6x squared plus 9. Now, graphing this is not really going to do a whole lot for you. In most cases, it's going to be really hard to see what's going on just by eyeballing the graph. If you'd like, you can graph it just to sort of get an idea. At least, hopefully, it will look like your function is approaching some sort of value. And it is. You can tell it looks like as x is getting increasingly large that the y value is sort of leveling off. But remember, you can always go to your table. And I'm set to ask. So if you go to second window for your table set, my independent variable is set to ask. That's just because I like to put in values. It doesn't usually help me to have the calculator choose values for me. So you might want to make sure that that's happening. But you can look at extremely large values of x. I mean, even just think about smaller values of x, like 10. Well, the y value at that point is 1.1938. Let's say you went up to 100. Well, now you're at 1.1714, 1,000. You can see now that the values of your function as x gets increasingly large are starting to all level out to a certain value. And here, once you get to x equals 10,000, well, now you're really getting to that 1.16 repeating. And as you continue to increase that 1, 2, 3, 4, 5 to 100,000, you're going to find that you're going to get that same answer every single time. If you hover over it, you'll get more decimal places. So you can see that you're getting slightly closer, but not by much. Each time, I'm guessing you're going to get one more 6 after the 1 6 in your decimal. So you can, verify what's going on with your answer on your graphing calculator if you want to check it if you're not sure. You can always go for that. I think it's always a good idea to look at both, especially if you're not sure. Questions on how to use your graphing calculator to verify a limit, or what we did here in example 2? Okay. Let's work on a few different ones then, different types. Not types, but more interesting functions, I guess I should say. Example 3. Oh, and I also think these are good because it reminds you of trig derivatives. So this will be the limit as x approaches 0. The sine 3x divided by the tangent of 8x. I'll move my light. It's too much brightness. Okay. Now, you got to know your trig function values in order to know whether or not you have an indeterminate form. It's very important, especially for 0, that we know our trig function values. So this would be the sine of 0 divided by the tangent of 0. Technically, if you're not sure, and I really hope that by Calc 2, this would be something that you would just know. You can always put them in your calculator. Whether you're in radians or degrees is not going to make a difference in this case. The sine of 0 is 0. The tangent of 0 is 0. Make sure you're double checking these. Students really get into the habit of just automatically doing L'Hopital's for every single exercise. You've got to verify that you actually have an indeterminate form first. Otherwise, you're going to be changing your function and the value of its limit. Okay, so you do have an indeterminate form here. So we're going to use L'Hopital's rule to rewrite the function. So I'm going to take the derivative of sine 3x, and this is also going to use the chain rule. So remember that we're going to just take the derivative as though we just had sine x, but then we're going to chain on the derivative of the inside function. So if this was sine u, the derivative would be cos u. So when we chain on the derivative of the inside function, we'll be chaining on the 3. So this is going to be 3 cosine 3x. And we'll do the same thing for tangent. The derivative of tangent u is secant squared u, and then the derivative of u would be 8. So 8 secant squared 8x. And again, you got to know your trig function values. Otherwise, you're not going to be able to find this limit, but also you won't know if you still have an indeterminate form. If the secant is bothering you, you can always switch it back into a cosine. You can write secant squared as 1 over cosine squared. But either way, the cosine of 0 is 1. Think about your unit circle here. It's on your trig sheet, but here you are at 0. And at 0, you're at the point 1, 0. And remember that your cosine function is controlled by the x value. And your sine function is controlled by the y value for whatever point you're on. So when you're at the angle 0, when theta equals 0, the cosine is 1 and the sine is 0. And of course, the tangent is controlled by the sine over the cosine. So the cosine of 0 is 1. If you'd like, I can fill this in. 3 times 0 is still 0. If you want to do secant 0 and then square it, if you feel like that makes it a little bit more accessible, then do that. But the cosine of 0 is 1. And then the secant of 0 is just 1 over the cosine of 0. Remember that the secant of theta is 1 over the cosine of theta. This is just a recall. So you can always use that. If you know the cosine of 0 is 1, 1 over 1 is also 1. So you'll have 8 times 1 squared. And the value of your limit now you can see is 3/8. But that's another one you can always check in your calculator. Always make sure you're in radian mode. It's always a good idea. Your graph will look much different if you're not in radian mode. Your graph will look crazy. A question on example 3. Okay. You're going to see so many different types of functions. That's why when I go through examples for L'Hopital's rule, I try to give you a bunch of different ones for derivatives that maybe you haven't seen in a while. Because I don't want it to be like, well, what the heck? Inverse tangent x. And again, we have to know our trig function values. Verify that you have an indeterminate form. Clearly the numerator is 0 when we let x be 0. But then in the denominator, you're looking at the inverse tangent of 0. Well, if you're looking for the inverse tangent of 0, you're looking for the angle whose tangent is 0. Well, you basically just did that up here. You told me that I told you the tangent of 0 was 0. So if I'm looking for the angle theta such that tan theta equals 0 is what you're looking for here, that angle would also be 0 because the tangent of 0 is 0 and the inverse tangent is the angle. So you do indeed have an indeterminate form. You're now going to have to apply L'Hopital's rule in order to simplify this down to a form that is not indeterminate. And I'm going to go through here and verify. Oh, I don't even need to verify actually because it's definitely on here. Your inverse tangent formula for the derivative is on the derivatives and integrals sheet. It's written as arctan. I think I've been using inverse tangent notation because your book doesn't use the arc notation. Some books love it. Some books interchange them, which I think is ideal. I don't actually see it all on here. There's probably one in here and I'm just not spotting it. But oh yeah, there it is. It's inverse notation. Up to you, but I mean, hopefully you know that arctan and inverse tan are the same thing. So it's u prime over 1 plus u squared. You've done so many of those integrals though lately in doing that in reverse, but I'm going to remind you again. So d du of inverse tangent u is u prime over 1 plus u squared. So this is a recall, but it's also on your derivatives and integrals sheet in the content tab of our D2L page. Okay. So we are going to use this to take the derivative of the inverse tangent of 4x. And of course, we'll have to also take the derivative in the numerator. So we're going to take those derivatives separately. The derivative of x is 1. And the derivative of the inverse tangent of 4x is going to be, and we're going to have to write this as a quotient in the denominator. We'll simplify it in a second. If u is 4x, u prime is 4. And then 1 plus u squared would be 1 plus 4x quantity squared. If you want, you can kind of separate that out a little bit more so you can tell what's going on with your complex fraction. So you don't even have to completely simplify this. You can work on it the way it is. I find that students don't like to work on complex fractions the way they're written, so you can rewrite it. Before I do that, does anybody have questions about how we rewrote the limit using L'Hopital's rule or the derivative? Okay. Wonderful. So we'll take the limit as x approaches 0. And then if you would like, instead of dividing by this fraction, you can multiply by the reciprocal. So instead of dividing by 4 over 1 plus 4x squared, you can multiply by 1 plus, and then 4x quantity squared is 16x squared, and then 4 will be in the denominator. And then the 16x squared, when you evaluate x at 0, will give you 0. So you'll just have 1 plus 0 over 4, which is 1/4. Again, this should be easily seen in your graphing calculator, probably on the graph, but you can also go to the table and just send x to 0. You remember at the way beginning of Calc 1 when you were working on limits in the first chapter and you had to make all those little charts and you had to like approach 0 from the left and approach 0 from the right and show your limit value as you were approaching from both sides was the same? Technically, you could do that here. I'm going to ask you to show your work using L'Hopital's rule, but you can always use methods from Calc 1 to verify your work or to kind of do your own little check. There are a lot of different ways to verify your limits. Okay. Questions on example 4? Okay. Let us then do another infinity over infinity form. So this is the limit as x approaches infinity of the natural log of x squared divided by x to the 4th. If you'd like, you don't have to, but you might want to rewrite your natural log using that power rule for logarithms by bringing your exponent out front. I'm going to give you another recall just because we're going to use this rule quite a bit, probably throughout the section, maybe not like all the time, but definitely more than once. The natural log of x to the p is p times the natural log of x. Now that's assuming that your power is only applied to x. That does not work if it's being applied to the whole natural log. Okay, so if the whole natural log is being taken to the p, you can't use that power rule. The p only is applied to the x. So you can rewrite this as twice the natural log of x over x to the 4th. Just showing that you have an indeterminate form, it's not going to really matter, but you're going to find the derivative is easier to simplify if you just have natural log x instead of natural log x squared. All right, so you have twice natural log infinity divided by infinity to the 4th power. If you're not sure what the natural log of infinity is, well, think about your natural log graph. Now, it's going to go there very slowly, but you can tell as values of x get increasingly large, the value of y is going to keep going up. It might seem to you like at some point it levels out, but it doesn't. It's just going to keep going up and up and up forever. So the natural log of infinity would be considered infinity in this case. And x infinity to the 4th, again, infinity. So you have the special form infinity over infinity. Questions before we apply L'Hopital's rule? Okay. So we're going to take the derivative separately in the numerator and in the denominator as x approaches infinity. Remember the derivative of the natural log of x is 1 over x. So if you want to write it as twice 1 over x, fine. If you want to write it as 2 over x, also fine. Note that if you had left it in the original form where you have natural log x squared, you would just be taking u prime over u. So you would have gotten 2x over x squared. You would still simplify to the same quantity. It would just be one more step to simplify your derivative at that point. And then we have 4x cubed. And we are going to rewrite this function. We can move the x down into the denominator. You can cancel between the 2 and the 4, and you'll just get 1 over 2x to the 4th power. And then you can apply the limit again. Because you have a constant in the numerator, you know you don't have an indeterminate form, but you would say that you have 1 divided by twice infinity to the fourth power. You haven't used this in a while, but there's a rule from Calc 1. It's an algebra rule, but actually, no, technically it's a Calc 1 rule, where if you're taking the limit as x approaches infinity of 1 over x to the k, you are getting 0. So what's happening is when you divide by infinity, you're taking a constant and you're dividing it by this number that's getting increasingly large as x gets increasingly large. The denominator is getting increasingly large. When the denominator gets increasingly large, the quotient is getting increasingly small because you continue to divide by a number that gets smaller and smaller and smaller. So what's happening is this quotient ends up going down to 0. And if you want to just think about this as being 1 over infinity, that's fine. You can think about it being the same way, or you can just go straight down here to 0. Same idea there. So when you're dividing by infinity, assuming your numerator is a constant, the quotient is getting increasingly small and heading off to 0. Questions on this one? You're going to be seeing a lot more of this type of thing as we move into chapter 8, where you're kind of comparing quantities and just kind of using your own logic to think about one quantity being larger than another, or what happens as that quantity approaches infinity, or as the value of x approaches infinity. Wonderful. There's one we maybe don't have to go through, but I kind of wanted to do it just because it involves rewriting a trig function. So let's do that one now. And then we'll move into another type of example. So this is going to be the limit as x approaches pi over 2 of 10 secant x plus 11 divided by the tangent of x. I also think that anytime we're doing trig functions, it's good for you. I'll remind you of your unit circle. So when you're at pi over 2, you are at the 90-degree mark at the top of your unit circle. And when you're here in your unit circle, you're at the point 0, 1. Remember that your cosine function is the x and your sine function is the y. So when you're evaluating the secant of pi over 2, you're evaluating 1 over the cosine. So if you were to do 1 over, if you really want to use cosines, which you might, 10 times, and then when you evaluate this, instead of writing secant pi over 2, you could write 1 over the cosine of pi over 2 plus 11 divided by, and then the tangent of pi over 2 is the sine over the cosine. So the tangent of pi over 2, if you'll remember from trig, now I feel like I want to draw you a tangent graph, is going to be, okay, I'm going to write it down as sine over cosine, but I want to remind you of what this graph looks like. And I'm also I'm really glad we did this because I did want to talk about this anyway. I can get another example prepared for it. But notice that in both of these cases, you have a situation where you have 1 divided by 0. You might not have seen this before in Calc 1, but thinking about your tangent graph, you have vertical asymptotes at plus or minus pi over 2. And then remember your tangent graph is positive, and it kind of goes up through here, and then it repeats itself as it heads back, starting from negative infinity to the right of pi over 2. So what happens is the tangent of pi over 2 we would always consider to be infinity. Now, with the cosine of, I'm sorry, 1 over the cosine of pi over 2, again, you're in a 1 over 0 situation. You can think about it graphically if you'd like. I mean, here's your cosine function. Goes like this. There's pi. Here's pi over 2. So you can see why your cosine would be 0 at that point. Remember that your secant function is built off your cosine function as a guide. So remember in trig, gosh, I feel like I'm taking you guys down memory lane. When you were drawing your secant functions, you would always draw asymptotes where your cosine had x-intercepts, and then you built your secant graph based on your guide graph for your cosine function. So this would be like y equals the secant of x. Well, you're seeing the same behavior happening, that as you approach pi over 2, depending on which side you approach from, you're either going to be going to infinity or negative infinity. So same with your tangent. Depending on which side we approach from, you're either heading to infinity or negative infinity. This is what happens when we divide by 0. There's like an 80s song called Divide by 0. It's not a good thing to do, but we would generally consider a constant divided by 0 to be infinity. This would give you a situation where you had 10 times infinity. Plus or minus is not going to matter in this case, whether it's infinity or negative infinity. There's no difference there. You're still going to have this indeterminate form. Because it's indeterminate, we're going to need to use L'Hopital's rule. I don't think you guys would have a problem going through this and saying like, okay, this is problematic. I can't get actual values. I just want to make sure that we can make the leap from I'm dividing a constant by 0 and I'm getting a quantity of infinity. Before I proceed with L'Hopital's rule, are there any questions about the indeterminate form itself? Okay. So we're going to go ahead and use L'Hopital's rule. We're going to take the derivative separately in the numerator and in the denominator. So remember that the derivative of your secant u is secant u tangent u, and then the derivative of 11, of course, is going to be 0. So you're going to have 10 secant x tangent x, and then the derivative of tangent x is secant squared x. Now, if you use it in this form, you're going to notice that you will still have an indeterminate form. Go ahead and cancel out, though, that common factor of secant. See, get rid of one of your secants, and we'll rewrite this as the limit as x approaches pi over 2 of 10 times the tangent of x divided by the secant of x. Now, you're still going to have an issue here as far as your tangent over secant is concerned, because you're using this same logic. Whether it's happening in the reciprocal or not, you're still going to end up with this indeterminate form. If that happens and you can't actually get it to simplify just by taking derivatives, you're going to have to just rewrite the function. So at least you've gotten rid of this plus 11. You don't need to worry about that now. It looks pretty similar, except now you've switched these positions. If you try to use L'Hopital's rule again, you're going to end up with secant squared x divided by secant x tangent x, and this is just going to keep flip-flopping. So you're going to have to find a way to rewrite this function. And a lot of times the easiest way to rewrite your function is to use sines and cosines. So I'm going to think about this as the tangent being sine over cosine and the secant being 1 over cosine. We'll see if we can eliminate one of these factors that's causing us to have an issue here as far as the infinity over infinity is concerned. So your tangent of x is going to be sine x over cosine x. And then instead of writing your secant in the denominator, write it as cosine in the numerator. And then you can get rid of these cosines. And then you'll have, if you want, you can pull the 10 out front, up to you. 10 times the limit as x approaches pi over 2 of the sine of x. And we know that the sine of pi over 2 is 1. So your limit is 10. And I mean, I would even suggest that if you're stuck at the beginning and you're kind of like, I'm not really sure where to go with this, I'm not sure what to expect. The nice thing is you can always look at your graphing calculator and get a good idea of what you think the answer is going to be. And at least if you know that it's heading to some number, you kind of at least know what you're looking for, and it sort of gives you a guide for how you're going to get there. Questions on this one?
Nope. Everybody's nice and quiet today.
Very quiet. I know, my family's gone too, so all of a sudden got super quiet here, which you know I love. Okay, then let's talk about some other forms for indeterminate rules. Oh, and by the way, we probably already used this. I'm trying to think, did we use this? No, we did not use this. I'm going to write it because it's in your book and you might find it helpful at some point on your homework. So I'm going to give you these. They're on page 314, but they're just sort of results that come from examples that were given in your text. And you might find them useful, even if not here, somewhere in chapter 8. You might want to highlight them. ln x divided by x to the n. If x is approaching infinity, that limit is 0. So this is a result that you can use. We'll talk about it in a second, but you might want to also give this result for x to the n divided by e to the x equals 0. This is jogging my memory. There's something else that I wanted to share with you. You might find that when you're working on these limits, having results like this that sort of give you general functions and which one's growing faster might be really helpful to you if you're kind of stuck evaluating them. The natural log function, I graphed it on the other page. We talked about how it goes up, but slowly. It doesn't actually level off. X to the n is going to increase more rapidly. Because your denominator is increasing more rapidly, it's getting larger faster. So as x gets really large, your denominator is getting really large, your quotient is going to be getting increasingly small. So that's why this result exists. E to the x is always going to grow faster than x to the n. So if you have e to the x in the denominator and x to the n in the numerator, and x is approaching infinity, then your limit is going to be 0. I think I have, don't want to forget about it. I do have a result that I was going to share with you at the end. Take it out now so I don't forget about it later. Okay. Excellent. Let's go over some different types of indeterminate forms then. Let's see what happens when we have, oh, you know what? Your book doesn't actually have what happens when you have infinity minus infinity, but I'm going to give you an example of it anyway. I'm not even going to write you formal directions for this. I feel like just seeing some examples is going to be better than having formal directions. I'm going to give you I'm getting to that point in my career where I totally need to redo some of these notes because I have all these little side notes that say, do this, do that, do that. And it's like a roadmap and it's nice, but while I'm in the middle of teaching, it's kind of confusing. Okay, example 7. So we're going to do some of the type infinity minus infinity now. So you're going to see we're also going to be using some rewrites like we had to do in the last example, but this time we'll be rewriting because we have a different type of function. So I'll give you one that's a little bit more basic to start. So the limit as x approaches 0 from the right of 10 over x minus 3 over x squared. So we talked in the last example about this quantity where you're taking a constant and dividing it by 0, and you're getting the result that's plus or minus infinity. So in this case, you can consider that to be an infinity minus infinity situation. And again, if that seems odd to you, think about what this would look like on your calculator. 10 over x is just that reciprocal function that's just being stretched out vertically. And as you approach 0 from the right, x is approaching infinity. But you could also graph this function in your calculator and look at what happens as you approach 0 from the right, and you're going to find that that function also approaches infinity. If you want, we'll even look at them. Let me get my interrogation lamp back over here. But if you were to look at these separately, 10 over x, when you graph it, you'll find that as x approaches 0 from the right, I'm going to remind you of what this looks like, just because it's been a while since a lot of you have seen these limits. As x approaches 0 from the right, you're on this side of the graph, and you're noticing that the y values continue to increase upwards towards infinity. That's where this infinity comes from. When you look at your other function, we're looking at 3 divided by x squared. You're going to see the same type of behavior. So as we approach 0 from the right, you're looking at the right-hand side of your graph. And as we approach this y-axis, the graph continues to head upwards towards infinity. That's where you're getting the infinity minus infinity situation. So if you're ever not sure, graph it. Verify that that's what's happening with your graph. Because I know sometimes this whole dividing by 0 thing, it's new and it seems extremely abstract to us just to create a rule for it and say, always do this all the time. That's where it's coming from. So this is a special type of indeterminate form. Infinity minus infinity is not equal to 0. So we are going to rewrite this function in order to try to get rid of that infinity minus infinity situation. And the way we're going to do that, and I'm going to pull the function out for a minute here to work on it, is to rewrite this as one fraction and see if we can simplify it down. We can get a common denominator in this case. I can write 10 over x as 10x over x squared, just by multiplying the numerator and denominator by x. And this gives me 10x minus 3 divided by x squared. Once you have this rewritten as one quotient, this is where you're going to apply L'Hopital's rule. You're not going to apply it here. You have to have a quotient in order to apply that. So you can go ahead now at this point and take the limit as x approaches 0 from the right of 10x minus 3 divided by x squared. Now, you're still going to get an indeterminate form in this case, but you're going to end up with 0 over 0. And if you're wondering, well, like, does it matter that x is approaching 0 from the right? In this case, it doesn't, because in the numerator and denominator, you have polynomials in both instances. So whether you're approaching from the right or the left, you don't have any discontinuities that are going to change those values. So if you were to let x go to 0, in this case, you'll have negative 3 divided by 0. And if you have negative 3 divided by 0, you actually no longer have to worry about this indeterminate form. Because even though we started out, sorry, I was thinking this was not a minus 3. I forgot about the minus 3 when I said you would still have an indeterminate form. You actually don't have an indeterminate form because you don't have 0 over 0. You have negative 3 divided by 0. And when you take a real number and you divide it by 0, in this case, you're going to get infinity. You have a negative. So we would say that this limit is negative infinity. You can always, once again, verify that in your calculator. I'm going to take this function, 10x minus 3, and divide it by x squared. And now, yes, it does matter that you're approaching 0 from the right, most likely, because you're probably going to see this split in 2 different directions. But when you graph this, notice that as x approaches 0 from the right, your y values are heading downward. So it looks like they're going up, but they actually end up going downwards towards negative infinity. So it actually, if you approach from the left, you would still in this case get negative infinity. But you might want to check that just to make sure that the sign is correct on your answer. But this is not indeterminate at this point. If you're just taking some constant dividing by 0, some constant that's not 0, then you can simplify this down. The light is blinding me. So you would actually say in this case that your limit is negative infinity. I know that I don't think we've actually had a limit be infinity or negative infinity in this section. It can happen. Just because we have an indeterminate form doesn't mean you always have to get a real number answer. Let's see. Okay. Let's talk about what happens if we end up with a very particular special form. It's actually very common. Let's do that. Example 8. So this is going to be the limit as x approaches infinity of x to the 8 over x power. All right, if you were to verify that you had an indeterminate form, you would get infinity. I know this always looks weird because we sometimes draw 8s instead of infinities when we're not thinking clearly. So having 8s and infinities in the same question was probably not a wise idea for me, but here they are. You have infinity to the 8 over infinity. Remember, when you're taking a quotient and you're dividing it by infinity, that quotient is getting increasingly small, assuming that your numerator is constant. So you officially will have infinity to the 0 power. Your constant divided by an extremely large number, the number is getting larger, your quantity, your quotient is heading off to 0. This is an indeterminate form. This was on the special list that I gave you at the beginning. Infinity to the 0 power. Okay. If you have a situation, and you're going to see this happen more often than you might imagine, and you're also going to see it in chapter 8, where you have an exponent in your base and not an exponent in your base, sorry, a variable in your base and a variable in your exponent, you're very likely going to need to apply this process. But in this case, you have this particular indeterminate form. In order to get rid of that, you're going to need to get rid of this variable that's in your exponent, because the base having your variable x heading off to infinity and your exponent, it's not going to work for you. There's a certain process that we're going to use to rewrite this function. I'm going to show you step by step how to use this, and then I'm going to show you another example using this just so that you see it twice. because I really want to make sure it sticks. Okay, so we are going to let, and don't skip out on this. I know sometimes when we write extra stuff, students don't want to write it. We're going to let y be the limit as x approaches infinity of x to the 8 over x. Now, the reason we're doing this is because we don't want to have a variable in the exponent. We want to get rid of it. The only way that we're going to do that is to apply a natural log on both sides. Remember, if I apply a natural log, I can use that power rule to bring the exponent in front of the function. I mentioned that power rule earlier, but that's what we're going to use now. So when we get to the end, we're going to have to remember that we applied a natural log and we're going to have to undo it. So let's go ahead and say then that if I apply the natural log on one side of the equation, I must apply it on both. This is very valid. I can also say that I have the natural log of the limit as x approaches infinity of x to the 8 over x. So what I do to one side, I can do to both. You also had a rule back in algebra that allowed you to either take the natural log of the limit or take the limit of the natural log. If I were you, I would rewrite this so that you have the limit as x approaches infinity of the natural log of x to the 8 over x. This is just going to be a series of rewrites until we get this down into a nice form where we can take our limit again without having to worry about it being indeterminate. Okay. Wonderful. Now that you have a natural log in front, you can use the power rule for logarithms to move your exponent in front of the function. So you are going to have the limit as x approaches infinity of 8 over x times the natural log of x. Does anyone have a question so far? Okay. So the whole point here was we wanted to get that variable out of the exponent. We've done that now. Now we can rewrite this and worry about actually taking this limit. Notice that if you took the limit now, you would have 8 divided by infinity, which is 0, times the natural log of infinity, which is infinity. You would still have an indeterminate form. You still need to use L'Hopital's rule. We just did a bunch of work to the function. None of it involved L'Hopital's rule. In order to actually evaluate this limit and get rid of the indeterminate form, we're still going to have to do that. What we're going to need to do, though, is write this in the form of a quotient. So you have the natural log of y is the limit as x approaches infinity of ln 8x divided by x. And then we're going to use L'Hopital's rule, take the derivative separately in the numerator and the denominator. But now it's in the form of a quotient, and we can do that. We need it written as f over g. So the derivative of the natural log of x is 1 over x. If you want to write that as 8 times 1 over x, you might find that simpler than writing it as 8 over x, up to you. And the derivative of x is 1. Okay. Now that you have taken the derivative in the numerator and denominator, you can go ahead and apply the limit. As x, you know what, I'm going to rewrite this one more time to make it super clear. This 1 in the denominator might look kind of confusing. You might want to just write this as 8 over x, and that might make it look simpler for you. As x gets increasingly large, your quotient is going to get increasingly small, all the way down to 0. So this is where we use L'Hopital. Now, don't say that the value of your limit is 0 because it's not. What you just found was that your limit was y, and you found that the natural log of y was 0. So if the natural log of y is 0, well, you're going to have to find whatever just y is if you're going to find the value of your limit, because you let your limit be equal to y. Remember that if you take both sides with a base of e, you can rewrite this as y equals e to the 0, which means y equals 1. Now, as long as you at some point wrote down y equals your limit, that's fine. You can just circle it and you're done. I'm just going to write down this result. The limit as x approaches infinity of x to the 8 over x equals 1. Again, something that you can look at in your calculator to just make sure that you're not crazy and everything is legit. I'm going to do one more like this. Oh, you know what? There's one that I wanted to do. It's not like this, but I don't want to forget to do it. So I'm going to do it real quick, and then I'll do the other one that's like this. The first one's super quick. I don't want to forget about it because it's kind of a good technique. It's a short question. It's just a good technique. The limit as x approaches 0 of x times the tangent of 1 over x. All right, so this would be...
Quick question. Is that a 0 or an infinity?
Infinity.
Okay, you said it.
You
said 0, but yeah.
I said 0?
Yeah.
Oh, sorry. I don't know why I would have said that. No, it should be infinity. Okay, so when you apply the limit, this would be infinity times the tangent of 0. The tangent of 0 is 0, and infinity times 0 is an indeterminate form. If you are wondering what the heck am I supposed to do in such an instance, if I were you, I would rewrite this as a quotient. Sometimes you're going to have to force it to be a quotient so that you can force it into a position where you can use L'Hopital's rule. So what I mean by that is you can leave the tangent 1 over x in the numerator, and then in the denominator, you can write x as 1 over x. So you're kind of like creating a complex fraction where there wasn't one. So instead of multiplying by x, divide by 1 over x. And it's not something we usually do, but it's completely valid. Now, if you're wondering how in the world is this possibly going to help me, well, you're going to need to use L'Hopital's rule because you're still going to be in a jam here. The tangent of 0 is still 0, and 1 divided by infinity in this case is still going to give you 0. A lot of times when you just rewrite and you don't use L'Hopital's rule, a lot of times you still end up with an indeterminate form, just a different variation of it. But in this case, we'll go ahead and use L'Hopital's rule to try to simplify this down. So we're going to take the derivative of tangent 1 over x. Remember, this is tangent u, so we're going to get secant squared u times the derivative of the inside function. So secant squared u times the derivative of the inside function. Now the derivative of 1 over x this is from Calc 1. If you have 1 over x, the derivative, we would write this as x to the negative first power, would be negative x to the negative second, which is 1 over x squared, negative 1 over x squared. So using the chain rule, you're taking the derivative as though you just have tangent u, and then you're multiplying by the derivative of the inside function. And then you're doing the same thing in the denominator. Taking the derivative of 1 over x, again, you're just getting 1 over x squared. The way that it's written now, you're not going to get anywhere because still you're going to have these zeros and you're going to have a 0 over 0 situation. So cancel those out and you're going to get the limit as x approaches infinity of the secant squared of 1 over x. And this will put you in a good position because when you let x go off to infinity, well, 1 divided by infinity gets you to 0. If you're like, how's that going to help me? Well, this is 1 over the cosine of 0 squared. The cosine of 0 is 1, as we discussed previously. Your limit is 1. That was such a good problem. I don't know how that ended up being an afterthought. Okay, technically I only have 2 minutes. I want to do this one last example. If you want to log off because you're like, okay, I cannot deal with any more of this, that's fine. You can watch the video later. I'll give you some time back on your async lecture. Those have been shorter anyway. You guys have lucked out with those. And then if you have questions on this, stick around for the office hour. All right, my last one is going to be the limit as x approaches 0 from the right of e to the x plus x to the 2 over x power. All right, so like I said, when you're seeing a base that has a variable in it and your exponent also has a variable in it, you're going to want to get rid of that somehow. And the way you're going to do that is by using a natural log. So you're going to let y be your limit. And we're going to go through this one a little bit faster because we've already done this process before. All right, so you're going to let y be the limit. Then you're going to take the natural log on both sides. And if you want to just do that inside your function, that's fine. If you want to even just skip a step and write the exponent first, that is also fine. So you're taking the limit of the natural log of e to the x plus x to the 2 over x. And you're going to do this a bunch of times on your homework, so hopefully you'll get very familiar with that. And then you're going to write this as 2 over x times the natural log of e to the x plus x. Now, chances are you're going to want to write this in more steps because it's very hard to jump around in these because there's a lot going on. But in order to use L'Hopital's rule, you will indeed need to write this as a quotient. Oh, we forgot to verify that it was even indeterminate, but e to the 0 is 1. And then 2 divided by 0 is infinity. Oh, that's our 1 to the infinity form. Okay. If you tried to do the limit again here, again, you'd still get an indeterminate form because you haven't actually applied L'Hopital's rule. But you would get the natural log of 1, which is 0, divided by 0, still indeterminate. But we're going to go ahead and apply L'Hopital's rule. And we're going to say, oh, I don't want to forget about my ln(y), just because I don't want to forget my answer is actually the natural log. All right, so we have the limit as x approaches 0 from the right. If you want to move the 2 out front even, that's fine. You don't have to leave it inside your limit. It's just a constant. You can yank it out. So we're going to apply this limit. We're going to take the derivative of the natural log and divide it by the derivative of 1. Remember, the derivative of your natural log is u prime over u. So we'll have twice. And then u prime is e to the x plus 1 divided by itself is e to the x plus x. And the derivative in your denominator is 1. And then you can go ahead and simplify that one step further. I'm just going to write mine as twice the limit as x approaches 0 from the right of e to the x plus 1 divided by e to the x plus x. And then you'll check it again. If you send x off to 0, e to the 0 is 1 plus 1, and then e to the 0 again is 1, and then plus 0. 2 times 2 is 4, and don't forget, that's just the natural log of your limit. If ln y is 4, then y is going to be e to the 4th. I'm going to unzoom that. Okay. I owe you like 3 minutes of your life back. I'm going to be recording a lecture for you on 8-6 and 7-7. I think I'll probably do 7-7, not 8-6, 7-6. I'll probably do 7-7 first because it corresponds to this. And then maybe in class next Wednesday, we'll do 7-6 and talk about 7-8. I don't know. We'll see. I'll kind of think about what would work best. All right, I'm going to post the asynchronous lecture on Friday. I always do. Like I said, last Friday, I didn't send an email right away because it just kept saying it was processing. It didn't upload for a while, so I ended up just forgetting about it. It did upload Friday. I double checked at some point, but just look on D2L if you're trying to get it done early and you're like, oh my gosh, she didn't email me yet. Just look and verify that it's there. Other than that, I'll see you Wednesday. We're still on schedule for a test on, I believe it's the 20th. Yeah, the 20th.
2 weeks.
2 weeks from today. I know it seems like a long time, but it'll be here before you know it. If you have questions, email me. I'll be on for another 16 minutes if you want to stick around. Good night. Becky, should I turn off the recording?
Sure, why not?
Okay. I never know if you have a question that should technically be in there. I don't want to cut it off too soon.